Welcome again to my signal processing tutorial series where we explore key concepts in signal processing and work through practical examples to enhance understanding. And in today's session, we will discuss about the energy and power of a signal. So we need to understand why these metrics are so important. So knowing the energy and power of a signal is not just a mathematical exercise. It is essential for understanding how signals behave and how we can use them and how they impact the systems they are interacting. So knowing the energy and power of a system is very essential in signal processing for several reasons. One in system design. So energy and power of signal is fundamental for designing efficient and cost-effective systems in electronics and telecommunication. Just imagine if you just design system blindly without having the knowledge of the estimate of the signal power. So you cannot achieve that cost effectiveness of your system. Another reason is spectrum allocation in wireless communication. Knowing the signal power is important for efficient spectrum allocation, right? Reducing the signal interferences. Also, in broadcasting or telecommunications, it ensures compliance with regulatory power limits for transmitted signals. So knowing the signal energy and power, then you can work within the regulatory limit. Also in signal to noise ratio calculation, so we know this metric is very important, right, which measures the quality of signal in the presence of noise. So for signal x of t, we define total energy normalized to a unit resistance as the integral of magnitude square with respect to time. We integrate with respect to time. And the magnitude square here means x of t times the conjugate of x of t, because sometimes x of t can be a complex signal. So the square magnitude defines the product of the signal itself and the conjugate. And the normalized power is defined as the limit as t approaches infinity and 1 over 2t integrating from minus t to t. Actually, we integrate over a single period because when we define normalized power, normally this is for periodic sort of signals. So we just concentrate on over a period and then we can check the limit as the time approaches infinity. So it measures the average strength and the power, normalized power. It measures the average strength of a signal over time. This is crucial for continuous periodic signals like sinusoid and like. And if x of t is said to be energy signal if and only if the energy is finite, which implies the power is equal to 0 from the previous definition. And x of t is said to be power signal if power is finite, which implies the energy is infinitely large. X of t could be neither energy nor power, but cannot be both at the same time. This is very important to take note. So moving straight to examples. Example 1, find the energy or power of the following signal. This is a sinusoid A cosine omega t, and just for a periodic signal like A cosine omega t, the energy is infinite, because just the signal keeps on moving indefinitely, and therefore the sum of the square magnitude will be blowing to infinity. And in that case, we can find the average power, which is the limit as t approaches infinity, 1 over 2t, and then we integrate over the limit minus t to positive t, the square magnitude. And in this case, we have a squared cosine squared omega t. So using trigonometric identity, which is cosine squared omega t, which is 1 over 2, 1 plus cosine 2 omega t. Now substituting the value of x, all right, x of t into the equation, and we have 1 over t a square over 2 dt, which is a square over 2. Why? Because the average value of the cosine to omega t is 0 over the period, so this is 0, and we just need to integrate 1 over 2, which is a squared over 2, and this is a squared over 2, all right? Because integrating dt from 0 to t, then we're getting t, and that cancel out with this t, and the result would be a squared over 2. So having a sinusoid of magnitude a, then the average power would be a square over 2. Example number 2, find the energy or power of the following signal, which is x of t, given by e minus alpha t, where t starts from 0 and alpha is positive. So again, recalling the definition of the energy, which is the integral from minus to plus infinity, x of t magnitudes squared, square magnitude of x of t dt. Okay, and substituting x of t into the equation, then we have a squared e minus 2 alpha t dt. So since t starts from 0, so then we integrate from 0 to a positive infinity as the value from minus infinity to 0, then the signal is 0. So then we have a squared into minus 1 over 2 alpha, which is coming from here, minus 2 alpha, and then e power minus 2 alpha t, evaluating between the limits. And so we have a squared over 2 alpha into the value when t is infinity, which is 0, and then minus 1 when the value of t is 0. So then we have 1 here, so we have minus 1, so minus 1 and getting 1, and this becomes a square over 2 alpha. Since the energy is finite, then the average power will be equal to 0. And example number 3, so find energy or power of the fluid defined by sum of rectangular pulses defined from minus 2 to 0, which is 1, and minus 1 between 0 and positive 2. So again, recalling the definition of energy, which is the integral of square magnitude minus to plus infinity, and thus the limit of integration would be the way from minus infinity to minus 2 is 0, so we just integrate from minus 2 to 0, which is non-zero and is equal to 1. So this is 1 squared, which is 1, and then integrating from 0 to 2, which is minus 1 squared, and again 1. So then we have 2 plus 2, which is 4 units. And again, since the energy is finite, then the average power will be equal to 0. All right. So just to summarize, knowing the energy and power of a signal is very essential in signal processing for several reasons, as these metrics provide critical information about the signal behavior, signal utility, and impact in various applications. All right. So please do not forget to share this video with others who may find it useful. Right. And if there is a specific topic in signal processing you would like us to prepare a tutorial, then let us know in the comments or via the email provided. Thank you for watching, and I will see you in the next tutorial.